Saxon Advanced Mathematics, lesson 17. You guys, I'm so sad. I just found out that my phone died like 15 minutes ago, and I was just teaching away, but it was not absorbing. And I don't know why, because I always set my phone to airplane mode when I'm teaching, because calls or texts even can sometimes break off the filming, the videotaping, video recording. But anyway, here I am. Okay, so I was in the middle of explaining this problem. I'm gonna start over again. This is proof 2, ready? So I'll just slide up my notes and start over on a separate piece of paper for you. All right, so what we were saying is that this is a second way to prove Pythagorean theorem, and it starts with these 4 triangles, 4 identical triangles. They're all right triangles. Like I said, they're meant to be exactly the same. We call the short leg A and the long leg B. And then we call the hypotenuse C in each one of them. All right? If we want to find the total area of the triangles, which we do, we're going to use this later. Okay, that's base times height. So we would say it's A times B divided by 2, right? For each triangle, that's the formula. But we have 4 of them, so we would multiply it by 4. Cancel, and we see that 2AB is the total area of all 4 triangles. All right, good to know. Hold on to that. Now we're going to take the 4 triangles and we're going to connect them in a kooky diagram. Let me number them just to help you follow what I'm doing. I expect you to be writing this down just because it helps you understand the story of what we're doing. Okay, so here's the first one. Here's the second one. Oh, pretend they're perfect and it's all even. But 1, 2, 3, 4. And now we can put the letters back on. The short leg is A, the long leg is B. We can go all the way around the rectangle. And then the hypotenuses, the hypoteni, are all in the center of the diagram, right? And just to help you see the difference, I'm going to kind of shade the diagram, right? There's this center square. The triangles go around the edge. There's a subplot to this proof, if you really want to be particular, that proves that this shape in the middle here is a square, although you'd never know it to look at mine, would you? But that's a perfect square. It's C on each side, and there's right angles here. We know that there's right angles all the way around the outside too. I'm gonna skip the subplot of proving that's a square because I don't want to confuse you too much in that. Now, we know that the total area of the triangles is 2AB. The total area of what I'm gonna call the inner square is C times C, right? So it would be C squared. Now, the outside, let's just do this. The total area of the triangles is 2AB plus the total area of the inner square is C squared, right? Now, what about this outside edge? That should be equal to the area of each side is A plus B units long, right? AB, 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 AB. So we can describe the outside edge as being quantity A plus B squared all around the edge, right? Okay, let's expand this and see what we get. Again, we're trying to work toward proving A squared plus B squared equals C squared. That's our goal. All right, we expand that binomial, which I hope you can do in your head at this point. If not, you can multiply it out. But I know that it's going to be a squared plus 2ab plus b squared. And now, look what I'm going to do. I'm going to subtract the 2ab from both sides. And we get c squared equals a squared plus b squared. That's exactly what we were trying to prove up on the other page. So this is another way to to prove that the Pythagorean theorem is true, and it helps you just get inside the head of people who are doing proofs. It helps you understand the thought process. It's in order to do a successful proof, it's very important to have a diagram and to go step by step in taking the details of that diagram and expanding them to what it is that you're trying to prove. I do not expect you to be able to develop a proof this complicated by yourself. I do want you to be able to follow along as I tell you the story, because understanding it will help your brain wrap itself around what the heck it is that we're doing here. What does this even look like, this doing of proofs? And I know I've repeated myself. I repeat myself a lot when I teach, and I'll tell you why. Scientists have found that in order to really record information in our short-term memory, we have to hear it 7 times before it actually lands firmly into our short-term memory. That's why, you know, with commercials on TV, they repeat themselves over and over and over. That's why, like, people will buy ads on social media, Instagram, and you'll just see it again and again and again. They're trying to hit that 7 times counter and land firmly in your brain. That's why I say the same thing more than once. I know you hear me. I just want to repeat it so it will land in 7 times. And again, that's not 7 times for teenagers or anything like that. It's 7 times for everyone. So interesting, right? And as a side note, in order to move from short-term memory to long-term, 10 years. No wonder you don't remember your times tables, right? It's hard. Okay, now we have covered all that I want to cover about these Pythagorean proofs. What I want you to do now is take a break. Go get something to eat, drink some water, punch your brother. Oh wait, I didn't say that out loud. Say hi to your brother, pet your dog, go for a little walk, but come back in within 15 minutes max, and I'll be ready waiting for you. Okay, I'm back. Are you? I want to show you, again, this was something that got lost on my video. Here's a little chart that summarizes what it is we're trying to do here. I'm just going to cover bits up instead of writing it all over again. Draw 4 squares. And in the first one, please write congruency postulates. These are the rules that we learned as to how you can prove that 2 triangles are equal. That's what this means. Congruency postulates is a fancy way of saying equal triangles. There are 4 ways that you can prove that triangles are equal, and we talked about them before. Side, angle, side, 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 angle, angle, side, which is the same as 3 angles, right? If you know 2, then you must know 3. And then the 4th way works only for right triangles, hypotenuse, leg. We talked about these before. We did proofs about these before. This is when you're trying to prove that triangles are equal. But what about situations where you're only trying to prove that the triangles are similar? And again, to remind you, similar triangles means that they have the same angles, but they have different length sides. Same angles, different sides. Here, everything's the same. Another thing I want to make, and that's why I put this little star here, another point I want to make is that the sides in similar triangles are different lengths, but they're always proportional. And we're going to use that little tidbit to help us. Okay, so if we're going just for similarity, not for congruency, this bar is set a little lower. We don't have to have such high standards, but we have similar standards that we have to meet. The most obvious is angle, angle, or angle, angle, angle. Obviously, again, if you know 2, you know 3. But this is exactly what we said similar triangles are. They have the same angles. So if you can prove that 2 triangles have the same angles, then you've done it, right? We can also use 2 of these other ones. We can use side, 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 or side, angle, side, these 2. But in these, we're not proving that the sides are equal. We're only proving that they're proportional. Write these words down. I know they don't make sense yet. We're going to work examples and you'll see what I mean. All right, so I'll let you finish copying this before I turn the page. It was so sad. I was teaching to no one. I keep checking my phone now because I'm really paranoid it's going to stop recording again. Okay, so let's take a look at an example. And I'm going to just write it over again. I'm going to get my paper. My scrap paper. My beautiful example has already been done, so I'm going to do it again. Okay, this is example 17.1. And John's drawn a lovely picture for us. It's this bow tie kind of a thing, like this. He puts letters at each vertex. And he tells us that angle A and angle E are the same. That's what that tick marks means, okay? He tells us to prove that, prove that triangle ABC, and then he uses this mark and says triangle EDC. All right, what I want to tell you is that this mark means congruent. Be sure to write this down. You're writing everything down. But if you just have the little wiggly without the equal sign, that means similar. So what John is saying is prove that triangle ABC is similar to triangle DEC. We don't have to prove that they're exactly the same. We just want to prove that they have the same angles, or in some way prove that they're similar, okay? So that's what that single booply boop means. We use the same format. At this point, I'm going to continue to write statement and reason, but if you just want to put an S on one side and an R on the other, I'm fine with that. The first thing that we know, so we record the information that we know both on our picture and down here. I'm going to color coordinate it so you can keep track of it. The first thing we know is that angle A is congruent to angle E, right? And that we know because it was given to us. All right. John didn't give us anything else, so we just have to stare at the picture until we figure something out. And what I'm drawn to is these vertical angles, because I know that vertical angles are equal, right? And so that I'm marking that in purple. So the next thing I say, I can't say angle C, because these are both angle C, but I can say angle ACB is congruent to angle ECD. And the reason I know that is because vertical angles are, I'm going to say equal. You could say congruent. That would be good too. But now I know that I've got 2 of the 3 angles. And if I want to be, I could stop right here and say, oh, right? I could stop right here and say that 3 triangle ABC is similar to triangle EDC because of angle, angle, which leads to angle, angle, angle. Remember, that's one of our similarity postulates is that if you can prove 2 angles are the same, then you know that 3 angles are the same, and that will do it for similarity. So that's what we did. We've got 2 angles, right? John told us one of them, and we used vertical angles to figure out the other. So we're done. We're done. We did it. Yay. That is a lot simpler than those crazy Pythagorean monsters, aren't they? Okay. Excuse me while I flip my books around. That's where I was when I realized I wasn't actually recording. So now I'm ready to move on. Example 17.2. There are 3 examples in all. Are you glad I gave you a break? Because this is requiring a lot of brain power, isn't it? 17.2. Another interesting picture. This one I see right away that these are parallel lines. As soon as I see parallel lines, do you know what I start thinking about? Transversals. We have one line that goes like that and another line that goes like that. Letters. All right, and we're supposed to prove that triangle ABC is similar to triangle DEC. So let's look, ABC, DEC. Okay, so this, it's like upside downy, isn't it? All right, well, let's see what we got. We'll start our list. And we always start by putting any given information onto the list. Statement and reason. All right, we know, because of these arrowheads, we know that AB is parallel to ED. And that is given. All right, what else do we know? Well, last time we talked about the congruency of vertical angles, right? So let's get that one on the list. Our second one is that angle ACB is congruent to angle DCE, right? Because these are the angles that match and these are the angles that match. So this is like a twisted triangle. And the reason for that is vertical angles are equal. You could say congruent, but I'm saying equal because it goes into your brain better. Okay. Now, we have to find another set of angles that match. And I keep thinking, well, John told us, he made a point of telling us these lines are parallel, and it makes me think of transversal. So I'm going to turn this a little bit so it looks more like a normal transversal to me. And I'm going to kind of extend these lines out, right? These are the 2 parallel lines. It helps me see what I'm looking at. And then this is the transversal that chops. Ooh, I made it messy. This is the line that chops, right? And so I know that it creates a pattern of large, small, small, large, right? So I go back and I look, I want that to be darker. I look at my diagram and I go, okay, where are the pairs of corresponding angles? I go, okay, this is cutting through, so I'm not gonna pay attention to that line. I'm just gonna pay attention to this line. And I see that this angle is the smaller, right? And this angle is the smaller, right? It goes larger, smaller, smaller, larger, larger, smaller, smaller, larger. So these 2 angles would be the same. And that is a great help to me because when I go back to look at my book sliding all over the place. Now when I look at my original triangles again, I see that I can say that angle B is the same, congruent to angle E, because, oh, I should have written, my numbering system went crazy, didn't it? Oh my gosh, this should be 3 and 3. Okay, I know this is true because transversals create equal angles. Equal pairs of angles, I'll say. Right? And now I've done it because I've got two angles in each triangle that I'm saying are the same. So now I can say triangle ABC is similar to triangle DEC. Remember, we want to be careful to keep the pattern of how we put the letters. It describes the same triangle. So I went from here to here to here, and that's the same as here to here, no, here to here to here. You know what I'm talking about. You have to make the flow match. And this is by reason of, if you have two angles, then you have three angles, and that proves similarity. So once again, we use the first postulate of similarity to prove our situation, all right? Sorry about the misnumbering, that's kind of crazy. All right, we have one more. And these example problems that I'm doing, these I would expect you to be able to create yourself. The Pythagorean ones I'll never ask you to do yourself. These I will. Example 17.3. We've got two triangles, and I'll draw them the way John has drawn them, and then I'll fix them. Okay, he says GHI 12, 15, 30 degrees. And then I see 30 degrees over here. Okay, I like what I see. I can see that these triangles have the same angle, but I don't like the way they're drawn. So I'm gonna redraw this one so that it looks like the big one, because it's too confusing otherwise. Okay, so now the 30 degrees is here. That means the 8 is up here and the 10 is down here. And this is the J and the K and the L. Okay, I'm gonna cross that out so I don't pay attention to it. All right, so now I can compare these better. And John wants us to prove that triangle GHI is similar to triangle JKL. Okay, this reminds me, it's the lower bar. It's not the 4 postulates of congruency, it's just the 3 postulates of similarity. And I have a pretty good feeling that because this time I've got sides, this time it's not going to be angle, angle, angle. It's going to be one of the side postulates. And remember, I don't have to prove that the sides are the same because they won't be, but I have to prove that they're proportional. So let's start our list. Statement. Reason. The first thing I'm going to say is that angle G is exactly the same as angle J. And I know that because it was given. That's a good reason, right? Now, I don't have any other information about the angles, do I? There's no vertical angles, there's no transversals. There's nothing to help me in that way. So I'm going to turn my attention to the sides, and I'm going to see if I can create some proportions with the sides. So I'm going to look and see if, first I'm going to say GH over JK. GH is 12, JK is 8. That's given. And then, similarly, I'm going to create a proportion for another pair. This time I'm going to say GI over JL equals 15 over 10. I'm going really slow in this. This is all also given. Now, if it's true that these two are proportional, then GH over JK should equal GI over JL. What I'm saying is that this is one ratio of sides, this is another ratio of sides, and if these triangles are similar, then these will be proportional. And I can test that by plugging in the numbers. 12 over 8 equals 15 over 10. If this is true, then I've proven it, but I have to do the math first. And so I say 12 times 10 is 120. Let's see if we can do 8 times 15 in our heads. 8 times 10 is 80, plus 8 times 5 is 40. 80 plus 40 is 120. So it checks. So it proves that they're proportional sides. So for my last step, and I guess I'll flip the page. Statements continued, reasons continued. Then I will say that the first triangle, GHI, is indeed similar to the second triangle, JKL. And what am I up to? I'm up to 5. And the reasons that I know that's proportional, my similarity postulate is side, angle, side, right? Because I proved that this side is proportional to this side is proportional to that side, and then they have an angle in between them. So it's proportional by side, angle, side, and what we like to say, because we're proving similarity, not congruency, we say similarity postulate. And now that we're doing both, if you were using side, angle, side in a congruency postulate, then you would say congruency postulate. All right, we have to make that distinction now since we're using SAS. Let me just show you. Since we're using these two postulates for both congruency and similarity, then in our proofs we should say which one we mean to use. Again, if we're using them for congruency, they have to be equal. If we're using them for similarity, they just have to be proportional. Okay, so be clear about that in your reasons. I really like, as you can see if you look at the book, I used the same level of detail that John uses in his work, and I think this is a really good level. It's not too wordy, but it's got a nice form. It's easy to follow. So I would like you to format your proofs to look as much like this as you can make them look. I haven't looked at the solutions manual lately to see what he offers there. But again, remember that you lay out the diagram, you list what given information you have, you add any details that you can figure out yourself, like we figured out vertical angles, like we figured out this transversal sheet, and then you look to see which one of these postulates is going to work for me. Am I choosing from congruency list or similarity list? How can I manipulate this information a little bit more to get to one of those postulates? That's all I have to say. I think that's plenty, don't you? That's lesson 17. That's all I have to say. Thank you. Goodbye.